Well, everybody, Mathman here again. And the last video we had was pretty dense, pretty intense. But I think it's pretty cool that you're able to use derivatives to get information, to extract information out of the function's behavior, its characteristics, through taking derivatives and looking at their behavior when the when the functions are zero, when the derivative is zero, and the second derivative is zero, and looking at the signs around the zeros of the derivatives, and being able to tell whether or not the curve is concave up, concave down, if you're at an extrema, whether you're at a minimum, either a local or absolute minimum, or local maximum or absolute maximum. Some curves are negative for the most part. An inverse parabola will go to negative infinity on both sides, and the way it's constructed, there could be some portion of the function that might be positive and crosses the x-axis. But there are an infinite number of possibilities with functions. And so, again, there are probably far more functions that the method won't be applicable to because of the fact that it's difficult to find factors, especially with high order functions and polynomials. But for most of the functions that we deal with on a daily basis are not very high order, second, third order. Nature doesn't behave in a complex way. Many of the empirical laws that have been derived for physical phenomena are inverse square laws. Potentials, like electrical potential, is just an inverse relationship. So the mathematical descriptors of nature aren't necessarily very complex. Boy, the Eagles have been really active today. I wish I had my telephoto camera going because they've been really going at it fishing in the lake today. But anyway, one thing we're going to look at today, I think this is really, really, really cool stuff. And it's very powerful. And it allows you to make relationships and connections that you wouldn't otherwise be able to. And so we're going to take a look at that. And that is using derivatives to make equations of between periodic functions like the sine and cosine function, such as exponential functions, and equate them to infinite series. And it's a very, very powerful method. It allows you to be able to take an infinite series, polynomial series, and use it to model periodic functions. One of the first to do this was a mathematician by the name of Fourier. We're not going to look at Fourier series at this point. We're just going to look at polynomial series, what they call a Taylor series. They also have a Maclaurin series, which is also polynomials. But the Fourier series uses sines, infinite series of sines and cosines. And he used that to model the violin. the sound of a violin. So everything that you hear in synthesized music, such as electronic synthesizers, are done with Fourier series. And Fourier first thought of the approach back in the early 1800s. I think it was just after the turn of the 18th century into the early 19th century. At first, many mathematicians were skeptical of the method, but today it's a very, very powerful. Oh boy, I really hate to use that term. Very, very powerful. I think I'm going to try and find some synonyms for that because we have a crazy man that uses that word. Very, very powerful. Almost every other word. So I think I'm going to try and find alternative verbiage for describing things. But anyway, let's get into it. I don't want to talk too long, but I think this is so cool, so neat. And we're also going to do Fourier series. So Fourier series are so cool. They're just so neat. This is where calculus and mathematics it blows your mind that the world is behaves in mathematical ways. So anyway, we're going to take a look at this. We're going to take a look at projectile motion, and projectile motion also was one of Einstein's uh, considerations when he was thinking of a cannon on a mountaintop and shooting a cannon fast enough, a cannonball fast enough to free fall around the Earth, and basically equating gravity to a free fall. So anyway, there's a lot of stuff we could. I mean, we could talk forever about this stuff. So let's take a look at how you can take a sine function and a cosine function, a trigonometric function, periodic, and make it into an infinite polynomial series. We're also going to take a look at exponentials, both a positive exponential, e to the positive x, and we're going to take a look at a e to the negative x. So let's get started, and I hope I have enough board space because these things can get rather lengthy. And we're going to try and find the best angle for this board. Uh, Again, I wish I had a little better board than this. Okay, I think you can see that. So here we go. Let's take a look. Now, what I'm talking about is, let's see if I can, I'm beginning to run out of ink, these pens. Let's take a look at the cosine function. So we're going to say the cosine of x. And yes, I do think that shows up. And what we're going to do is we're going to make it equate to an infinite series. So what we're going to do is we're going to create an infinite series with coefficients a0 plus a1 x plus a2 x squared. That's a power series, plus a3 x to the third plus a4 x to the fourth plus on forever, because that is an infinite series. But we don't need that many terms. All we need are enough or sufficient terms to be able to see the patterns that may arise as we take derivatives. So basically what we do is we take the derivative of both sides of the equation. So the cosine of x, the derivative of that, as we've seen in past videos, is minus sine x. And now the derivative of a constant, a naught, these are subscripts identifying the different coefficients. And that's basically what the problem is, solving for the coefficients. So a0 goes out, a1, we're left with a1, x, a1 plus 2, a2x plus 3, a3x squared plus 4x3 plus 5, a5x to the fifth, and dot, dot, dot. Then the next derivative is the derivative of the negative cosine, or negative sine, so that's negative cosine. You can see what's happening here, where because these alternate between sine and cosine, when we take the derivatives, we're not changing the functions that much. We get the original function back again, except in this case, we got a negative sign. But that goes away. After a cycle of about 4 or 5 derivatives, we end up back at the beginning again. You'll see that in a minute. So that next derivative is, okay, a1 drops out. We got 2a2 plus 3 times 2, a3x. And there's a reason why I'm writing it this way. Now, 3 times 2 is 6, and that's easy to see. But I prefer writing it this way, and I'll explain why later. Then we have plus 4 times 3, a4x squared plus 5 times 4. I'm sorry, this one I did wrong. I had to, there we go, x to the fourth, a5x to the third, dot, dot, dot. Okay, because I don't have much room on that side, I'm just going dot, dot, dot. If you're really going to be specific, I mean, you're going to go plus, dot, 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 plus, just to get the idea that you're still going on infinitely. This series just goes on forever. All right, so let's take the next derivative, which is negative cosine. So negative cosine is sine x equals, okay, the next term, this 2a2 drops, and we got 3 times 2a3 plus 4 times 3 times 2a4x. See, our x's are going down in power, and our coefficients are increasing in magnitude by what we'll end up seeing is a factorial. Now we have 5, let's get this pen right, 5 times 4 times 3, a5x squared, dot, dot, dot. And then the derivative of sine is cosine. So we got cosine of x. And you see now we've repeated. You see we started off where we began. Okay, so here we have whatchamacallit, we have cosine of x is, we got to take a look at these derivatives. 4 times 3 times 2 a4 plus 5 times 4 times 3 times 2 a5 x plus, and here we have minus sine, the next derivative, and we can go on how many times we want, just taking more and more derivatives. And you can see the pattern here that's arising. That is going to be this term, because that one drops out, and x. So we have 5 times 4 times 3 times 2 times a5 plus, and we have 6 times 5 times 4 times 3, times 2 a6 x plus blah, blah, blah. All right. I just brought one term in over again. And so we have cosine of x, and that's minus because we got a minus sign there. And this is going to be, we're going to have 6 times 5 times 4 times 3 times 2 a6 plus, now we could go on forever like this, okay? And look how full this board is. It looks like a mess, but it really isn't, because we're going to say what happens when x is 0. Okay, so we look at this. Geez, that didn't come out very well, did it? When I'm losing, these pens are losing it. When x equals 0. All right, so this first one is all those terms go to 0, and x is 0. All those x's go out, and you got cosine of 0 is 1 equals a naught. And this, the sine of 0 is 0. So there is no term for a1. So a1 is 0. A2 is negative 1 equals 2. A2. And this one here, 0. Sine of 0 is 0, so there's no a3. So we got 0 equals 3 times 2a3. And we have 1. Cosine of 0 is 1 equals 4 times 3 times 2 a4. Okay, 0 again. And we got a minus 1. So a5 is 0. 5 is 4 times 3 times 2 a5. And negative 1 equals 6 times 5 times 4 times 3 times 2 a6. Okay, so that's what we're looking for. We're looking for this for all of the coefficients. I want to get the screen back. That's the one thing about this particular deal, that whoops. All right, I'm sorry. why isn't this? Okay, that did it. All right, now I see there's a little glare here, so we're gonna try and twist that. I think you can see the board better that way. Okay. Now you can see here what I've been doing. I've been taking the derivatives. I first set up an initial equation for the cosine of x, and I said that cosine of x is going to be equal to this polynomial, this infinite polynomial. But I don't know what the coefficients are for that polynomial, so I just assigned dummy coefficients, and then I'm going to solve for them. So I kept taking derivatives to isolate each of the individual coefficients, A5, A6, A4, 3, 2. And then I set x value to 0, and I would get values for the different derivatives, and I would also get I would also be able to isolate a single coefficient, because all of the parameters, all of the coefficients that have x's will be 0 when you set x equal to 0. So what we ended up here is now these different values for the coefficients. Now, what we're going to do, I'm going to have to erase this. If you needed more time to take a look at that, you can rewind and stop the film and take a look at it at your leisure. Okay, so now A1, and I don't need these guys anymore. I'm going to be solving for the coefficients. Okay, remember our initial boy, what's wrong with this thing? Is starting to. I think I let it sit in the air too long. Well, let's take a look at another pen. Okay, so what we had was is equal to A naught plus A1x plus A2x squared plus A3x to the third plus A4x to the fourth plus A5x to the 5 plus forever. But when I did those derivatives and isolated the individual coefficients by setting x to 0, I get A1 equals 1. A2 is 0, negative 2 A2. Okay, A3 is 0, 1 equals 4 times 3 times 2, 1, or A4. Okay, and A5 is 0, and negative 1 equals 6 times 5 times 4 times 3 times 2, 6. Okay, so I can erase those. And now I substitute back into that equation. So I got cosine of x equals 1 plus or minus 1/2 half a2 plus 1 over 4 times 3 times 2. Whoops, not a2, x squared, x to the 4th minus 1 over 6 times 5 times 4 times 3 times 2, x to the 6, and it goes on forever like that. So we're having alternating terms, positive, negative, positive, negative, positive, negative, forever. And that's the way it is. So now we've got our infinite series. That's basically what it is. Now, if we take notice of this, remember a naught is equal to 1, but a naught is a coefficient of 1, so 1 divided by 1. And you could say that this is 1 factorial, which is 1. What I'm doing is this. We're going to notice that all these terms over 1 factorial minus 1 over 2 factorial x squared plus x to the 4th over 4 factorial. 4 times 3 times 2 times 1 is 4 factorial minus x to the 6, 6 factorial. And it goes on like this, plus x to the 8th, 8 factorial minus x to the 10, 10 factorial, and goes on forever. So that's what I was talking about. If you take enough terms and you look for patterns, you're able to find relationships like this. So now our final relationship, I'm going to just write more. Okay. Okay, equals 1 on 1 factorial minus x squared on 2 factorial plus x to the 4th 4 factorial minus x to the 6th 6 factorial plus x to the 8th 8 factorial minus x to the 10 10 factorial plus, and it goes on forever. And that's our infinite series. Now we can consolidate this into a more compact form that allows us to write this even more concisely. Now, as a summation, now notice that the bottom terms are even number factorials. The powers are even. Here we could say this is x to the 0, and remember 0 factorial is equal to 1, 1 factorial equals to 1, 2 factorial equals 2 times 1, 3 factorial equals 3 times 2 times 1, 4 factorial, I'm just doing this for your benefit, 3 times 2 times 1, and so on. And so that recognition allows us to write this in a little more compact form. So we could say that this cosine of x equals n equals 0 to infinity. Okay, now let's take a look at this. Now I may need to work it out a little bit because I don't have papers in front of me that show me what to do. So we're going to figure it out. And the way I normally figure it out is trying to look at the pattern. So first off, we're going to have an x, and we're going to have a 2 times n, because when n equals 0, 1, 2, 3, 4, 5, and so on, 2n equals 0, 2, 4, 6, 8, 10. Exactly what we want for our exponents for x. So we got that down for n equals 0 to infinity, for n equals 0 to 1, 2, 3, 4, 5, and so on. Now, the bottom, we can do the same thing. We can say that this is 2n factorial. Okay, so if we have n, again, is equal to 0, 1, 2, 3, 4, 5, we have 2n equals 0, 2, 4, 6, 8, 10. And then 2n factorial is equal to 0 factorial, 2 factorial, 4 factorial, 6 factorial, 8 factorial, 10 factorial. Oh, and 10 factorial, that's a big number. That's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3. 5 factorial is 120. I have a story about a math teacher in 6th grade who was teaching combinations, and he wanted my daughter's class to work out a problem that involved 5 factorial steps. And these poor kids were working, it was a 2-hour test, and not one of them got it correctly. And I can understand why, because they were these 12-year-olds were trying to work out 120 different combinations by hand. Okay, so now we got one more thing. Notice we have positive, negative, positive, negative, positive, negative. This thing is alternating between positive and negative. So that also means that we have to add another term in here, a factor of -1. And we're going to say -1 to the n, because when we have -1 to the n, and we have n equals 0, 1, 2, 3, 4, 5, and so on, -1 to the n equals -1 to the 0, which is equal to 1. -1 to the 1 is -1. -1 squared is 1. -1 cubed is -1. -1 to the 4th is 1, and so on. So we got our alternating positive, negative, positive, negative, positive. And so that term now allows us to write this compact form for a cosine function. So that's it. That's our infinite series for a cosine function. Okay. And again, that's my artistic skill, drawing rectangles. So there we go. That's the cosine function expressed as a infinite series, and this is called the Taylor series. And often, when you're talking with real small numbers, when we're talking about delta x's that are very, very small, I don't know, let's say very little, very, very small. Cosine of x plus delta x is going to be approximately 1 minus x squared over 2. That's how many terms you could take and still be relatively accurate. So it's pretty cool because the more terms that you add, the better the accuracy. Now, if you were going to use this infinite series for representing a cosine, I didn't like how that wasn't really square. Um, the the more terms you want, the more terms that you add, the closer it's going to approximate this. And if you take a look at this in a spreadsheet, if you put the cosine function, and probably this is how they estimate the cosine in Excel, they have an infinite series program. They're not really calculating the cosine itself. But if you put in the cosine and various angles, and then equate it to this, you'll find that the cosine of x, uh, this becomes a better and better and better approximation as you add more terms. If you add 20 terms or 30 terms, the difference between this infinite series and cosine of x becomes very small. So it's a fun thing to do if you're really into this kind of thing. And I find it pretty cool doing that. And again, I'm going to take a second because I hate to not see this, what's on the screen. Okay, so that's it for the cosine. Now you can do the same for the sine function. And you probably might guess what that is going to look like already, because the sine function is basically 90-degree phase, out of phase with the cosine function. So it's going to give you, instead of even powers, it's going to give you odd powers. And let's take a look at this. So we're going to say sine of x is equal to a naught plus a1x plus a2x squared plus a3x to the third plus a4x to the fourth plus a5x to the fifth. You may be better at this than me because I like writing these terms out term by term so I can be sure I don't miss anything. And it's easy to miss things. This is something where you have to be very meticulous about because you can easily make a mistake. So now let's start taking our derivatives. The derivative of the cosine function is the cosine of x, and the derivative of the cosine of x is minus sine of x, and then we have the minus cosine of x, and we have sine of x, and cosine of x, and so on. Okay, now our coefficients are going to be, we're going to have a1, we're going to have 2, a2, This is going to be 3 times 2a3. This is going to be 4 times 3 times 2a4. This is going to be 5 times 4 times 3 times 2a5. And this is going to be minus sine of x equals this is 6 times 5 times 4 times 3 times 2, 8, 6, and minus cos of x equals 7 times 5 times 4 times 3 times 2, and we can go on forever. Okay, so we're going to set x equals to 0 again. X equals 0. So the sign of 0 is 0. So a naught is 0. Now cosine of 0 is 1 equals a1. Minus sine of 0 is 0 equals 2 factorial a2. This is 1 factorial. And this is 0 factorial. And I made it so that you can't read it. So we've got 0 equals 0 factorial a naught. This is 1 equals 1 factorial a1. We got 0 equals 2 factorial a2. We have minus 1 equals 3 factorial a3. 0 equals 4 factorial a4. 1 equals 5 factorial a5. And 0 equals 6 factorial a6. And we can do one more if we realize that this one is going to be sine of x, and that's going to be cosine of x equals, this is 8 factorial a8, and this is 9 factorial a9. So we got 0. Let's see. We got minus 1 equals 7 factorial a7. 0 equals 8 factorial a8. And 1 equals 9 factorial a9. Now, we've got our terms, our coefficients for the different terms of the infinite series. And so, and as you can see, they're going to be odd. So sine of x equals, now a0 is 0, so we've got a, well, let's see, let's write this out. This is where a1 equals 1 on 1 factorial, 2 is 0, a3 equals minus 1 over 3 factorial, a4 is 0, a5 equals 1 over 5 factorial, a6 is 0, a7 equals minus 1 over 7 factorial, 8 is 0, and a9 equals 1 over 9 factorial. So that helps us a little better in writing out the infinite series. And so let's write it out. Equals A1 is, okay, so we got x over 1 factorial minus x to the third 3 factorial plus x to the fifth 5 factorial. And I got to make room minus x to the 7 7 factorial plus x to the 9 factorial plus goes on for infinity. So now we've got the infinite polynomial or Taylor series for the sine function. And again, we can go the sine function, sine of x is equal to x, n equals 0 to infinity. Infinity. All right. Now, here we've got an x, and we're going to have 2n plus 1. Okay, because when n is 0, 1, 2, 3, 4, 5, 2n plus 1 is 1, 3, 5, 7, 9, and 11, and so on. So you could see how our our exponent there gives us the odd numbers that we want. And that also, we got odd number factorials, so we're going to say this is 2 to the n plus 1 factorial. Remember, this goes in the bracket. We got to be careful about our nomenclature because we don't want to say 2n plus 1 factorial. It would look like somebody could misinterpret it. So you put the brackets around the 2n plus 1, and then the factorial of that. So you operate here first, and then you operate the factorial to it. Now there's one more piece. Again, we got the alternating plus, minus, plus, minus, plus, minus, and so on. So what we want to do is write n minus 1, 2. I think 2n is nope, that's going to be plus 1. So we alternate. We want to alternate. So let's see if this is correct. So when n equals 0, 1, 2, 3, 4, 5, 6, 2n plus 1 is going to be 1. This is going to be 3. This is going to be, let's see. No, you know what? I think all we need is just n. See, this is what I say about figuring these things out. N. Okay, so when n is 0, let's see, we got negative 1 to the n is equal to 1. 1 is minus 1, 2 is 1, 3 is minus 1, 4 is 1, 5 is -1, and 6 is 1. And that gives us the alternating pattern we want. So it's just simply -1 to the nth power. And there you go. And it doesn't look too different from the cosine function that we worked out, but it's just this way. It's the odd numbers. And you can come up with combinations. Remember the tangent of x equals the sine of x over the cosine of x, and you can then find the different coefficient or the ratio of the different expressions here, and you can find all kinds of really neat things. You can have different identities, trigonometric identities represented in polynomial form using infinite series. So there are a bunch of things that you can do that are pretty cool with this. I just think this is beautiful. I honestly do. I just think uh, how beautiful that is. It's really neat stuff, and it gives you an ability to do stuff, make approximations, and make it. For example, I have a video that I put on. Now you're going to be able to follow that video. It was the proof of the Euler identity. Okay, so um, that was done. The way I did it was taking a look at these infinite series and um, constructing the necessary um, relationships to give you the Euler identity using these infinite series and combining them. Okay, so now, as I promised, we're going to take a look at E. I wish this thing drew better. E to the x. Now let's see, E to the x. There we go. I think you can see. And we're going to say E to the x is a naught plus a1x plus a2x squared plus a3x to the third plus a4x to the fourth plus a5x to the fifth plus blah, blah, blah forever. Now, the interesting thing is here, the derivative of e to the x is e to the x. Unlike the trigonometric functions, the cosine and sine, the cosine, the derivative is the negative sine, and then the derivative of the negative sine is the negative cosine, and then you cycle around after 3 or 4 derivatives, and you come back to the beginning. Here, this is always going to be e to the x. So the derivatives here for e to the x is e to the x. And so that's going to be well, this one is for a naught. So this is a1. E to the x equals 2 factorial a2, a1. E to the x equals 3 factorial a to the third, e to the x equals 4. I'm cutting out some steps. I could write everything out. I can write out all of these derivatives. It gets very tiring because I know that this is what's going to turn up. E to the x again is 5 factorial. E to the x equals 6 factorial a. So, and they're all positive. Now you can go on forever this way. Now you set the x equals 0. So all the terms that have x will go out, and we'll leave you with these coefficients. Now, this is always going to be 1. So e to the 0 is 1. So 1 is going to be a 1. 1 is going to be 2 factorial a2. And we could say this is 1 factorial. 1 equals 3 factorial a3. 1 equals 4 factorial a4. 1 equals 5 factorial a5. 1 equals 6 factorial a6, and so on. And now you've got your infinite series. And a naught is 1, because e to the 0 is 1. Those are all zeros. A naught is 1. So e to the x is going to be, let's rewrite that, e to the x equals 1 plus x over 1 factorial plus x squared over 2 factorial plus, they're all positive, x to the third over 3 factorial plus x to the fourth factorial plus x to the 5 factorial plus x to the 6 factorial plus forever. And that's your Taylor expansion or Taylor series for e to the x. And we could write this as x to the 0 over 0 factorial, okay? And that will help us with writing out the compact form, the summation sign. So e to the x, then e to the x then equals from n equals 0 to infinity, x to the n over n factorial, because when it's just n equals 0, 1, 2, 3, 4, 5, then you've got n factorial is 0 factorial, 1 factorial, 2 factorial, 3 factorial, and so on. So we have a nice compact form. And everything is positive. See? So there's no need to have a term in here for -1 to the n. So that is not necessary. This is all we need, is x to the n over n factorial, and then sum it over. And again, for this one, this series, I did a little better with that box, didn't I? This expansion, you're going to find that this works better. Some of these, what they call convergence. We talked about convergence with series and sequences. Some of these converge faster to the function than others. For the trigonometric functions, you don't need as many terms to get a very accurate representation. For e to the x, you're going to need quite a few terms. You may want to carry it out 20 or 30 terms to be able to get a pretty close approximation of e to the x. So the rate at which these functions converge does differ. Now, one last function that we're going to take a look at is e to the minus x. And just remember, we've got, now writing these things, remember, we've got the sinh equals e to the x minus e to the minus x over 2. And now we got these, we can use infinite series to combine, and we can find polynomial Taylor series for the sinh of x. I wasn't precise here. So now, knowing that we've got these values for e to the x, and we're going to do e to the minus x now, you can then combine those and find an infinite series representation for the hyperbolic function. So here you've already got a lot of power to represent these various functions in polynomial form. Okay, I'm just going to do this last one. This is going to be a little bit more elaborate. E to the minus e to the minus x, again, equals a naught plus a1x plus a2x squared plus a3x to the third plus a4x to the fourth plus a5x to the 5 plus and forever. Okay. Now we start taking derivatives. Well, this is slightly different. We're going to see that this is going to be minus e to the x to the minus x. This is e to the minus x. This is minus e to the minus. Now you see the difference. We're going to have alternating values because we have a minus sign there in the derivative. And so we're going to have, this is going to be 1 factorial a1, this is 2 factorial a2, 3 factorial a3, 4 factorial a4, 5 factorial a5, and e to the x equals 6 factorial a6, and so on. Now we set x equals to 0. That's what allows me. It's this here that allows me to take that shortcut, because every other term then goes to 0. So this is all that's going to be left when we put x equals 0, having taken these 6 derivatives. So now we have this one up here, which is 1. So 1, we got minus 1, 1, minus 1, 1, minus 1, 1, and so on. And this one's 0 factorial a naught equals 1 factorial a1. This is 2 factorial a2 equals 3 factorial a3 equals 4 factorial a4 equals 5 factorial a5 equals 6 factorial a6. And you can see my arm's starting to get a little tired. I'm getting sloppier. But now we can solve for those coefficients, a naught through a6, and look for patterns. So a naught, a1, a2, a3, a4, a5, a6 equals 1, over 0 factorial equals 1 over 1 factorial equals, this is minus 1 over, you see, minus 1 over 1 factorial. This is 1 positive 1 over 2 factorial. This is minus 1 over 3 factorial. Positive 1 over 4 factorial. This is minus 1 over 5 factorial. And positive 1 over 6 factorial. And now we can write out our infinite series. And we've got the functions here. All right. So we have, I just write it out, x to the 0 over 0 factorial minus x to the 1 factorial plus x squared over 2 factorial minus x to the 3rd 3 factorial plus x to the 4 factorial minus x to the 5. Notice all the odd terms are negatives. 5 factorial plus x to the 6, 6 factorial plus forever. Now we've got our infinite series for e to the minus x. And it looks a lot like e to the x, except for this alternating sign here with the negative going with all the odd terms, 1, 3, and 5, and so on. So now we can try again and see if we can come with a compact summation for this. N equals 0 to infinity, x to the n, all right, over n factorial. And that seems to work, doesn't it? 0, 1, 2, 3, 4, 5, and so on. And we're not missing anything. The only thing different is now we have to add that -1 term to alternate. So we got -1 to the n. Because when n equals 0, 1, 2, 3, 4, and so on, -1 to the n equals 1, minus 1, 1, minus 1, 1, plus 1, and so on. And so that's the only difference to get that negative sign in our alternating fraction. So here we have e to the minus x, a nice depiction of e to the minus x as a Taylor series. And now we have e to the x equals, remember our summation sign, we had x to the n over n factorial, n equals 0 to infinity. And remember sinh, we got sinh x, our hyperbolic function, is equal to e to the x minus e to the minus x over 2. And that would be equal to, well, we can use our n equals 0 to infinity, x to the n over n factorial minus, again, another summation, n equals 0 to infinity, x to the n factorial, -1 to the n, all over 2. So now we have a Taylor expression for the hyperbolic sine. And we can do this for the cosine and the hyperbolic tangent. We can do this for all kinds of functions. It's really, really pretty darn cool that you can do this. And now that you've got the ability to uh, come up with the infinite series for the sine and the cosine function, um, you can now derive a way to come up with the Euler identity. Because remember, what we're doing here is not it's only an approximation when we terminate the series at some point. When the series goes on infinitely, that is an expression of this function. We've just re-represented that function in terms of a polynomial. And so it's valid to take a look at the sine and cosine and use their polynomial equivalents to come up with the Euler identity. So that is something that now you can go back and take a look at my videos, and there's a video where I demonstrate how I can use this method to derive the Euler identity. It's one of the earlier ones. I just, for some reason, I just had the I don't know. I got the urge to uh, the urge to do that problem. I saw it online, and I thought, well, let me solve it and see if I can use this method to solve the Euler identity, and I was able to do so. So anyway, you may be able to do it too for fun. Give it a shot. But this is such cool stuff. It's actually beautiful. This is so beautiful. It's amazing, amazing stuff. And as we go along and we look at mathematics, and especially how mathematics is used in a descriptive way for natural behaviors, for example, empirical laws for gravity. We've got projectile motion, parametric functions, and when we look at the parametric functions, I think maybe that's the next video we'll do is take a look at projectile motion. I think that's pretty neat stuff, and it's exactly what they use. Uh, Napoleon used it for he was in charge of the cannons for the French army, and he had to calculate the trajectories for the cannons, and so he needed the mathematics, and he used projectile motion for that because he had a mathematical ability. The scientists still use those parametric equations for uh, rockets and other motions, projectile motion, bullets, and other objects that are forced, given an initial thrust, and then like a baseball, when it leaves the pitcher's hand, then that ball becomes a projectile and moves down uh, per projectile motion affected by gravity. So we'll take a look at that maybe next time. I think this was pretty cool stuff. I really enjoy these Taylor series. The Chlorine series, I think, is not too different. Instead of a to the instead of a, let's say a1, you got a naught plus a1. You have x minus 1 plus a2 x minus 1 squared plus a3 x minus 1 to the third. And you set x equals 1 for the zeros. And you can come out, for example, the sine of um, uh, well, let's say e to the different functions. There are different uses. For example, e to the x minus 1 would be then e to the 0 when x equals 1, and so on. You got different situations where a Maclaurin series may be more appropriate than a Taylor series. But I think that's about the only difference, is the fact that they have this polynomial term in there instead of just an x variable. I think that's what differentiates Maclaurin from Taylor. And there are different series. For example, you can find f of x equals a summation of n equals 0 to infinity of sine theta plus cos theta, and this infinite series a to the n. You do the same thing. This is a Fourier. I don't know if I have it entirely written down. For a series, but it's an infinite series of sines and cosines rather than polynomials. And that's what they use for Moog synthesizers and all synthetic music, um, square waves, electronics, for simulating different waves, like triangular waves and square waves, and you can even use that to simulate a sine wave. Um, so anyway, uh, we'll take a look at a Fourier series later on in this little course that I'm giving. But anyway, I hope you found this interesting. I hope you found it fascinating. I thought this was one of the really cool things that I learned in Dr. Pine's math class, is that you could represent these functions as infinite series. I really thought that was so cool. So anyway, this is Mathman wishing you all well and stay safe from COVID. Please don't drink bleach. And I don't think anybody who would be watching this would be foolhardy enough to do that. So hopefully, but anyway, we still have a ways to go, and I hate to think that anybody is taking undue risks. So anyway, be safe and healthy. Thank you, and until next time.